Okay, so now we're going to see how we can visualize data using the pyplot module in the matplotlib library. So we're going to start by looking just at some simple plots, how to use this module, and then we're going to apply that to the data we've been using in the previous lecture and create an animation. So basically, we're going to write code to create the different frames in our animation, and then we can just create an MP4 file with all the different frames. So let's start with simple plot. Suppose that we have this file, which is just a simple set of numeric values. Sometimes we have these kinds of files, very simple files, which has the tuberculosis infection burden in Portugal for different years, starting with 1990, in number of cases per 1,000 inhabitants. So this is the year, this is the estimate of the tuberculosis burden, and these are the confidence extremes of the confidence interval, so the lower bound and the upper bound for the estimate. And we want to plot this data. So the first thing we need to do is to load this into memory, and we're going to load it directly into a NumPy matrix. This is very easy to do. If you have a text file that has numeric values there, you can use the load text function from NumPy. There is actually other arguments that you can give here. Say you need to skip some header rows, you need to change the separator between the values or something like that. But for this particular one, we just need to use load text and load the file. So this data object here will be a NumPy array with this shape. So 4 columns and 1 row per each year. And now to create a chart to plot this data, we need to import this pyplot module from the matplotlib library. So you can do import matplotlib.pyplot. Of course, this is a very large name, so it really pays off to give it an alias, and typically it's PLT for pyplot. So now we can use this function from pyplot figure to create a new chart, a new graph to plot things in, and we can either just call it like this, so without any arguments, or we can put some extra arguments. You can put the resolution, the size, and things like that. So I usually use fig size. This is the size of the figure, because it allows you to specify the width and the height, and this allows you to control the aspect ratio of your plot. So usually you don't want things very square, or depending on what document you want to put them in, you may need them to be narrower or shorter, something like that. And now for plotting, we can use the plot function. The plot function simply takes in the x values, the y values, and you can use a string to specify the display that you want. So in this case, the x values will be the years, which are the first column in our data. So from data, we select all the rows and the column of index 0. This is a vector with the years, because our data matrix has these values in the first column. Then we want to show the second value here, which is the estimate. And this is in column index 1. So we select all the rows, column of index 1, and we write a black line. This K is for the color, black, and the dash there is a line. Now we do the same thing for the lower bound, which is the third column, but we draw it in green, and the upper bound in red. We can add a title, TB infection load for Portugal, and show the graph. So if you do this, you get this in your console, which is where usually the plots appear by default in this version of Spider. There is a new version of Spider that has actually a tab above the console where you can see the plots, but you can select if you want them to appear in the console or over there. So this is the aspect, the look of this, because we drew the upper boundary in red, the lower bound in green, and the estimate in black. In alternative, you can also use this function savefig to save your file. Okay, so instead of showing the plot, or alternatively, if you are doing this in outside Spider, so if this is a standalone script, you need show to actually create the window and show the graph. If you're using Spider with the IPython console, then you don't need show. If your script ends and there is some plot in memory, the IPython console will capture it and show it. So if you're just doing a quick thing like this to look at the data, you don't need show. But usually what is more useful is to use savefig. So the savefig from the pyplot module allows you to save your plot to a file. You write the name of the file and the extension. For example, here I saved as a PNG. And then you have some additional arguments that you can add. You can just leave the rest by default, but I usually add these two. This dots per inch will control the resolution. The default resolution is usually not very good. I think it's 50 dots per inch. So I increase it to 200 to get a better looking plot. And the bound box is the frame around the actual plot. So between the end of the image and the plot, and I put it usually tight so that the plot part occupies as much as possible inside the figure. So if you do this, you can save the image and then you can put it in some document and use it for whatever you want. So in general, when we're automating data processing, we want to save the plots in the end so we can insert them in our report. Now you can choose different kinds of representations, either by changing the string there. This format string has lots of different options. So if you have some knowledge of MATLAB, you'll probably recognize this format string. It's the same kind of thing. You can use the dashed line, for example, for this one. This one is with the axis here, green axis, and red circles for the upper bound. Or you can specify additional arguments, for example, the thickness of the line. In this case, I drew this with 4 pixels in width, and these ones with 2 pixels in width, so I'm controlling different thickness. You can do lots of different things with plot, and also you have different styles. So this is the default style, which is a bit ugly and old-fashioned. You can use more modern styles. For example, I like Seabourn. You have many different styles there. If you can look up the documentation online and see what styles you have and how they look like. But if you do this first, so in pyplot, you say that you want to use this style, Seabourn, so plt.style.use, and then you get this more modern look for your plots. You can do also different kinds of plots. I'm just going to illustrate this with a bar plot. So in the bar plot, you have the X values tell you where the bars are placed, and then you need to specify the height of the bars. So in this case, the X, the position of the bars, is the years, the first column, and the height of the bars is the second column, which is the expected infection load. So these bars here. Then we can do the same thing with the lower bound and the upper bound. And in this case, with the bar plot, we need to offset a bit the position of the bars so that they don't overlap exactly. If you want to stagger them, you need to add or subtract some fractional value here so that they are displaced a bit. Note that when we don't specify colors and so on, plot will automatically cycle through a set of colors. So each bar or each series will be represented with a different color. This is the classical look, the default look. This is the Seabourn style. Okay, so basically with plot you put in X and Y, and then you have other arguments for the look of the series, including labels for the legend and lots of other things. We're going to see some examples of that. For the bar function you have similar things, only you need to specify the X value, the position of the bar, the height and the width of the bar also. So now let's look a bit more in more detail at tuberculosis. We were using a very simplified file with data for Portugal only. But actually, if you go to the World Health Organization site, you can download this data and you have a more comprehensive file with data for many different countries. And the format is like this. You have the country name, the ISO 2 and ISO 3 codes, the numeric code for the country, then you have the region of the country, the year, and then you have the population, the estimated load, the lower boundary and the upper boundary, and other things that you have there too. So this is a very large file that has data for many different countries. And you see that the same country appears many times because each row corresponds to 1 year per country. So what we need here is the ISO 3 code for the country in the 3rd column, the year, which is in the 6th column, and then these 3 columns here, the estimated loads, the lower and the upper bound, so columns 8 through 10. But we need to remember that when we are indexing these in Python, we are counting here with the first column being 1, but in Python the first one is 0, so all of these indexes will be shifted when we look at this in arrays. So we need to read the CSV file. Let's read it to a list with all of these rows, because that's we're going to see the function that we'll use for reading the file, and that is the way the function provides the data. But then we need, if we want to plot the burden for a specific country, we need to extract a matrix with the data for that country. And so we'll need an additional function to get us the data for the country, and then we can plot a specific country like that. So let's see how to read the CSV file. We're going to use this library, CSV, so this module, because it has this reader function that we can use to specify the file, the delimiter used for the different fields, the character used for quoting strings. Note that we have everything that is string is quoted with double quotes here, so we can specify the double quotes as the quoting character, and also we can tell the reader what to do with the other values. So basically we want to consider that quoted values are not numeric, but the not quoted values are to be converted into numbers. So this way we have not only a function that parses the file, but also converts everything nicely. And the way this works is we open the file, the CSV file for reading. We give the file object to the reader, so the reader goes through the whole file and outputs an object that is an iterator. It allows us to go through the CSV file row by row. And for each row, it will give us a list with all the values in that row. So basically, this is something similar to the idea we followed in the previous lecture, where we created that function to read every row. But this iterator basically can loop through all the file and give us all the rows. If you use the list function here, what the list function does is it goes through every element of whatever object we give the list function and produces a list with all the outputs. So this is a simple way of reading this file and getting a list of lists in which the first element is the list of all these values, the second list is a list of all these values, and so on. So you can see here, as when we test, we get our table of data by loading data from this CSV, and the first element of our table is the first row in the file. So this is basically just the header row here with the names of the different columns. The second row is the first one for Afghanistan, and you can see that the strings are there as strings, so everything that is quoted in the CSV file is retained as a string, but those values that do not have the quotes, that are not between quotes, these are converted into numbers. So we already have everything converted from string to number, those values that we need as numbers. And we have the first row of the table here, the second row, and so on, after the headers, which are here in the beginning. So now what we need to make it easy to plot our data is to have this auxiliary function that receives as arguments the table with the whole data set, so all these this list of all the rows, and the ISO 3 code for a particular country. For example, if we want Portugal, we can specify PRT. And this function will start with an empty list. For each row on this table, so for each of these lists here, it will look for the ISO 3 code that we specified in the third position. So if the the element of index 2 on this row is the code that we specified, then it found an entry for the country that we want, and it will append to this matrix the year, the estimated burden, the lower bound, and the upper bound. So this is a tuple with the 4 values, and this will be appended to this data. So this list will actually be a list of tuples with 4 values each. And when we convert this into an array, since all the tuples have 4 values and we have a list of them, NumPy figures out that this is a matrix with n rows and 4 columns. So it gives us this matrix, which has for each year the estimated burden, the lower bound, and the upper bound. And now it's easy to do the plot, because to create the function for plotting a country, we just need to provide the complete table. Note that I'm always providing the complete table to these functions, because the alternative would be for each function to load the data. But reading from the hard drive, from files in the hard drive, is much slower than operating with values in memory. So in general, it's a good idea to load everything into memory and then work with everything in memory, except only if you are dealing with so much data that memory cannot store it. But since modern computers typically have 32 gigabytes or 64 gigabytes of RAM, it's very hard to find problems where you're dealing with more data than that. So this is why we do it like this. We load the data once, and then we use the same data structure for the different functions. So in this case, plot country will receive the whole data, the code for the country that we want. It uses the previous function, this country infection, to get the matrix corresponding to that country. And then we create a new figure for plotting. We plot in black the estimated value using the first column as the years. Then we use the lower bound in green, the upper bound in red, the lower bound in green. I just switched the order here, but it's indifferent. And then we put the title there. So in this function just creates the plot. If we want to save, we can save it here. If you want to show or something like that, we can do it outside the function. So the way to use this is to load the data, use the plot country function, and then if we want, we can save the plot file. And this is the example using the Seabourn style here. Okay, so now that we covered the basics, let's go back to Gapminder and do something a bit more sophisticated. So we want to plot relations between different countries. And one way we can do this is to look at the trace over the years of each country. For example, suppose that we have Portugal, Germany, Spain, and China here, and we want to look at how life expectancy, which is here in the y-axis, changed over the years. when plotted against the per capita gross domestic product. And this one is in a logarithmic scale here. So you can see that there are some loops here, and then things sometimes go bad, but in general, everything goes up there to the top right, which is where everybody lives a long time and they are fairly wealthy and they can live well. So we have this, this trend here. But we want to create a function that we can use in a generic way for doing these kinds of plots. So this is one possible solution for that problem. We use this plot indicators function where we give a matrix with the x values. So each column of this matrix will correspond to the values of some indicator for each country that we're going to use for the x coordinate. Then we also give a matrix with the indicators for the y coordinate and the labels, which are the names of the countries. So the labels are in the same order as the countries in the column. So the first label corresponds to the first column in matrix X and the first column in matrix Y. Another thing that we need is sometimes it's useful to plot some axes in the logarithmic scale. For example, comparing GDP without logarithms will be a bit strange. So we can add these optional arguments here, or these parameters with default values, which is use a logarithm for the x scale or for the y scale. And in our function, what we can do is we create a new figure, and then we loop through all these labels, so the different countries. And we use enumerate because we also need the index in order to find the appropriate column in the x and the y matrices. And we also, when we do the plot, we also add this argument here. So we are specifying that the label for this series is the name of the country that we are looking at. So when we loop through these labels, we put each name as the label of each series. This is what is used by plot when we create the legend of the figure to put each color in the corresponding country. And also, if x log is true, so if x log, we set the x axis on a logarithmic scale. If y log is true, we set the y log axis in a logarithmic scale. Okay, so now let's see some examples. We can test our function like this. So this, I don't know why this is out of alignment, but we set the style using Seabourn, and now we load the data. We create a list of countries here, for example, these four: Portugal, Germany, Spain, and China. A list of years, we want from 1900 to 2009 in this case, and we get the indicator values of gross domestic product and population, so that we can use the we can compute the per capita gross domestic product. Okay, so I was missing one here, which is the life expectancy. I don't know why I deleted that one, but okay, so we need this one too. So we get the three different indicators for the same countries, the same years, and now we can do different plots. For example, we plot on the x-axis the per capita gross domestic product, on the y-axis the life expectancy of these countries, and putting the x on a logarithmic scale. So this is the chart we saw here. The gross domestic product in a logarithmic scale, the life expectancy there. But we can do different things. For example, gross domestic product on a logarithmic scale here, and population. So this is per capita gross domestic product, and population on the y-axis. And here we can see it's a problem when we're comparing countries like Portugal and even Germany with China. We get everything scrunched down here because China has a huge population, and the chart becomes a bit strange. But we can add here the logarithmic scale to the y-axis too, and now at least we can see something, although it's all pretty much squeezed. But when you see on a logarithmic scale, we can see that per capita GDP increased a lot faster than population. So this is an example of how we can use the functions we saw in the previous lecture, where we store our data as a dictionary of dictionaries, and then that function to extract matrices of specific years, and we create a sort of semi-generic plotting function where we just plug in the indicators that we want, if we want logarithmic axis or not, and we plot the graph. So this is also a general advice for this kind of problems. If you see that you are doing several different graphs for some report, for some work that you're doing, it's a good idea to create a function that where you generalize the things that vary, so what kind of values you have on each axis and so on, but where you retain fixed things that you want to remain constant. For example, the look of the graph, the aspect ratio, the colors and things like that. Because this makes it a lot easier to make a uniform look in your reports and the output of your data processing, because then you fine-tune everything in that function, and then you just use the same function for whatever plots of the same type you want. This can save you a lot of work when you're automating these kinds of things. Okay, so let's take one step further and create an animation. One way of trying to see how the countries developed over the years is to look at a time series as an animation. So we see 1 year at a time, and that way we can easily use 3 indicators at the same time. So we can use the X and Y coordinates for 2 indicators, and the third value can determine the size of the marker that we're using, because we won't be drawing a line, but just animating, moving the marker on the plot. We can do this by creating one image for every year, and then we have a few hundred, say 100 or 100 and something images on the drive. We just combine everything into a movie, and so we can create an animation like this. So the first step for this, we're going to decompose this into different functions. We can create a function just to draw one frame. So basically we get the axis. This is the plotting object where we draw the actual values. So this one has the plot function there where we can draw. And the reason for providing this one to the function is that we can do everything else with the plot outside this function, say set the different axis scales and the kinds of scales and colors or whatever we want, and then call this one just to draw the circles. So this will be the axis object we're going to use. These are the values for the X coordinate, the values for the Y coordinate. In this case, they are just arrays, so one value for each circle that we're going to draw, and the area of the circle. This is the third indicator. The colors, these are all vectors of the same size. So the first value of X corresponds to the first value of Y, the first area, and the first color. The alpha option here is for transparency. So alpha is an opacity measure. Alpha of 1, it means that it's fully opaque. Alpha of 0 will be invisible. If you use an alpha of 0.5, there is some transparency. This is sometimes useful when plotting different series that can overlap, because if you use transparency, you can still see where they overlap. You don't have one value hiding another. And now what we do here is for each index here in the colors, or for it's the same index for all the arrays, we can get the X value from the corresponding index in the axis, the Y value there, the size we'll get from the area here, but the size must be an integer value. This is a size in pixels and it has to be integer. And then we use plot in this way. In this coordinates, x, y, we'll draw a circle. We'll fill the circle with the color. This controls the size of the circle, we use the transparency there, and this is the color we want to draw it in. So let's see an example of how we can do this. We can create an image. We get the current axis, so GCA is get current axis, and this is the place, the axis in the figure where we are drawing our data. In some cases, you can have multiple plots in the same figure, so you could draw your data into any set of axes. But we just get this object of the axis that allows us to do the plot, and this is the one we send here to this function. Now we create we rescale the population, so we're starting from this part here. We already did this. We already loaded the data. We have a list of countries. We got the indicators for the countries and so on. But there is this small problem with the population of China, because if we don't change a bit, in this case I take the square root, because China has so much more population than the rest. If we don't do this, China gets a very large circle and kind of obliterates the rest, or otherwise we cannot see the rest. So I rescale the population there, and now I draw the circles. I use the per capita GDP of the 1950 for the X value here. So this is the row of index 50, all the columns for the 4 countries. I use the life expectancy too of the same year and the scaled population of the same year. So this is the X values, the Y, and the size of the circle. I use the colors I specified here that I don't have them here, but are these: red for China, green for Portugal, yellow for Spain, and black for Germany. And this is the result. So I draw the circles. I just add this scale, logarithmic scale, to the GDP axis, to the X axis. I put these limits. So this, if you use Y lim and X lim, you can give a tuple with the lower and upper bound for the axis. So for life expectancy, it's between 0 and 100, this axis here. And for the per capita GDP, it's between 100 and $100,000. So for the X here. And now I can save the image. So this is the basic function we have for drawing a list of countries using 3 indicators for a specific year. So we can draw each country in the position given by the X and Y indicators, and then draw a circle of different size, in this case with the population. Note that this is not actually the population, this is the square root of the population, because if we were actually using the area of the circle proportional to the population, China will basically cover everything, or we cannot see the others there. But this is just to get the general idea here. Okay, so now to create the animation, we need to create a function to loop through all the years and save each individual frame. But we also need to give that function all the data we want to represent in the chart. So we're going to give it a list of the different years because we want them in the title and so on. And we are going to give a dictionary specifying how the axes will be created. So, and for this we need to specify the values, so give a table with the different values. We need to specify whether or not we want a logarithmic scale. We need to specify the label for the axis, the name that will get there if we want to write it. What are the limits? And also we need the colors for the different countries. So this is one thing that we need to think about a bit, but the idea is that these axis values will be a dictionary that has X, Y, and area. So these are the 3 different values that will be represented. Each one of these entries has another dictionary that has the data, which is the table of the values, the label, whether or not it's logarithmic, and the limits. For area, it will ignore the label, the logarithms, and limits because these are only useful for X and Y. So let's experiment a bit and think about how we're going to do this. This would be an example of the list of colors that we give to our function. So the colors here will be a list like this. We want green for Portugal, black for Germany, orange for Spain, and red for China. And now we create this dictionary where the X entry, so what goes into the X axis is the data, is the per capita gross domestic product, the one we computed before. We set the islog entry to true so that the axis is on a logarithmic scale. And we provide these limits between 100 and 100,000 for the chart. And this is called GDP per capita for the x-axis. And the same thing for the y-axis. So I have the data is life expectancy. It's not a logarithmic scale. It's between 1 and 100, and it's called life expectancy. And then the third entry is just the area, the data as the scaled population. So this little trick we did here of computing the square root and dividing by 200 so that we can get circles with a decent size in our chart. Okay, now we create the images using these dictionaries. So how does this function, how can we implement it? We start by creating a new figure, and I set the size here, so 15 by 10. Note that this is in inches, but it's a bit arbitrary. It's not actual inches. What determines the final resolution of the image is these dimensions in inches and the dots per inch. So basically we have 2000 in height and 3000 in width because each inch is worth 200 pixels. So this you can have an estimate of how what's the resolution of each image. Now we get the axis, so we can send to the circles function. And now for each year in this list, we get the year and the index of the year. We will clear our graph, so this clear area deletes everything that's already been drawn on our plot. We set the title to the year. Note that the title must be a string, so we convert the year to a string because the year is a number. And now we draw the circles for that year. So the data that we need is for the x-axis. We get the x entry into this axis data that we received. We look at the data entry there because the data entry has the metrics we got from our previous function. So this get indicator values, the one that extracts a matrix with the countries and the years that we ask. So we put in this matrix for the x-axis, and we give the row of index IX, so the row corresponding to the year, and all the columns there. The same thing for the y value, but we go get that from the data on the y value. And for the areas, we do the same thing with the data for the area entry. So this dictionary is specifying what to use on the x, y, and the size of the marker for our different indicators. Now we set the limits for x and y on our plot to the limits that are provided here in this dictionary. So the limits for x, the limits for y. This is what we filled here in the limits. Here I think I forgot to set the label, but we could set the label for the axis to these values here. And then we check if we want logarithmic scale for the x or the y and set the scale. And finally, we save the figure. So basically, during this loop, we are clearing the chart, setting the title and drawing the circles, setting the limits and the logarithmic scale, and saving the figure. Now we need to save the different images in order. So we're going to use this formatting string here, this F string. You can experiment with this, but this is a very convenient way of creating strings with values. If you precede a string with an F, then everything that is inside brackets will be evaluated by Python. For example, this IX will be considered to be actually this variable, and we can get the value there. And furthermore, we can specify if it's a number or string or something like that, how it will be represented in our string. So this, you can look at the documentation for the formatting code. This is those things that it's very hard to memorize, but it's easy to look up when you need. So what I'm saying here is that I want 4 leading zeros, or so I want an integer with 4 digits with leading zeros. So this will give me, when ix is 0, it will be 0, 0, 0, 0, then 0, 0, 0, 1, 2, and so on, and always with the leading zeros. And this allows me to create a set of images with always the same file name format and these zeros here. So I'm joining this with the images in order to write everything, save all these images into the images folder. And this is just the other arguments that I use for the resolution and for the bounding box. Okay, so this is the function that loops through everything and saves all the plots. And since it takes a few seconds to generate each plot, I also put a print there with the year. This is something I don't usually do, so you rarely see a function that prints everything, because in general it's useful to have functions doing things silently. You don't want your console to get filled with rubbish or noise just when your code is running. But if you have something that takes a long time to run, for example, this can take about 2 minutes to run, it's useful to see if everything is going well. So if I print here at each iteration, I can see that it's writing the images and it's running and it's doing its work. So this code generates the images file like this, 00, 001, and so on. And then we need to create a video from these images. This is something you don't have to do it with Python. It's actually a lot easier to do with either with video editing software if you want to. I generally use FFmpeg. It's a useful program, at least in Linux. It's easy to use, and you can just look up the internet what kind of parameters you can add. This is the example for the actual video I'm going to show. So I set the frame rate. These are the images that I'm looking at. I'm looking at numbers with 4 digits, .png. So it will go through these in order, and then I use the codec for compression, and I resize everything because this requires the image size to be a multiple of 2 and so forth. Okay, so there are a few details here, but you can find these recipes easily online, and it's easy to convert images into a movie. So this is the MP4 file I saved, and this is the result. So you can see we start in 1900s. You can see at the start of World War I, and then that dip was the Spanish flu there. And then as we start World War II, you can see life expectancy in Germany decreasing a lot, but then things recover. Then we can see the famine in China about 1959, 61, but then things seem to go better. And you can see the progress. So first life expectancy increases a lot, and then GDP starts increasing and the countries start to catch up. So this is one example of how you can use plotting to automate the generation of a large number of images, and then you can combine those images into an animation, an animated GIF or an MP4 movie or something like that. That part is easy to do, and you can represent your data in different ways using animation. So one small detail, I'm now going to start adding some Python details when we are doing different things, but you're going to see this in some examples in the exercises. And we saw previously how we could include all our tests in a tests function, so that we wouldn't have all the tests run when we import a module. Because remember that when you import a module, when you import a module, you get the complete module is executed, and so that all the functions there are declared. But if you want your tests to run, only when you call the test function, then you need to put your tests in some specific function so that they are not run every time we import a module. But there is a different way of doing this, which is to use this condition to check if the name of your module is main here. Because when a module is run, when you run with F5, for example, then the name of the module will be main. But when the module is imported, the name value inside the module will be the actual name of the module. So the name of the file, of the Python file, without the py extension. So this difference, as the interpreter sets the name attribute either to the name of the file or to main when we run the file, allows us to check if our file is being run as the main file or if it's being imported by another file. So if you do something like this, if name, these are two underscores in the beginning and the end, because this is a special attribute that the interpreter is setting. So if this name is called main, also with two underscores, this string, this means that this module is the one being executed as the main module. So you can put here everything that you want to be executed when you actually run the module as the main module. So in this case, I'm reading the data, creating the countries, and creating the images for the animation. But if the module is imported by another module, then its name will not be main. It will be whatever name you saved the module into. And so this is not executed. So basically you can set all your tests or anything else that you want by adding an if name equals main condition at the end of your script. This way, all of this code is executed when you press F5 in Spider. But if you are importing the module, then the code is not executed because the condition is false. And that will allow you to specify code to execute only in the main module. This is useful because these kinds of functions that we created here for creating the plots and drawing everything, we created them specifically to do this at this time, so creating this animation. But they can be reused in different contexts. And if we do this kind of condition here, then we can safely import these functions into other modules if we want to expand on this code and implement something that reuses the functions we made here. So to sum up for today, we saw in this part how to do some simple plots. We are going to go back to plotting because we're going to do plotting several times when dealing with data. But we saw some simple plots, styles and colors. You have lots of different options for plotting, and also lots of different functions. I recommend you check the documentation if you're working with visualization. But the generic approach here is perhaps the most important thing for these two lectures. It's this idea that first you load the data and organize it internally inside your program. It's not a trivial task. You have to think how you're going to organize things, but then everything else will tend to be built around this data structure that you conceived at first. So then you're going to create auxiliary functions to select specific types of data, transform the way the data is stored and so on, so that it's most convenient for each particular functionality, for each particular task that you want to perform, plotting, computing, whatever, but it will all move around this central structure of your data. So in our case, for the Gapminder example, we created those dictionaries, those nested dictionaries, and then the auxiliary function to extract matrices of data for the countries that we want, and we built everything around that structure. So I recommend that you take a look at matplotlib, at the documentation on the site, because you have lots of examples there. And now we can take a short break. So I will start the Zoom meeting for anyone who wants to ask questions at 7 o'clock. Okay, so we have a 10-minute break now. Bye, see you soon.